Hi, I'm Peter Linder, and this is my Engineering Honors Capstone for Winter 2022. I'm presenting my work on the MFly Autonomous subteam. My project specifically was twofold, including a detect and avoid system and an unmanned ground vehicle. So first, some background. I'm the Autonomous Chief Engineer on MFly, where I work on a plane for the AVSI SUAS competition, which is a competition for autonomous flight with several mission tasks, including navigating a series of GPS waypoints, avoiding GPS-based obstacles, detecting and avoiding another UAV, searching for and classifying targets on the ground using computer vision, and dropping an unmanned ground vehicle, or UGV, which must autonomously deliver a water bottle to a target location. Some of these tasks have already been completed and others are being worked on by other people, which is why I chose to focus on detect and avoid and the UGV. So first, the detect and avoid system. My objective was to develop a cost-effective method to detect another aircraft during flight from a range of 50 to 100 meters. This range would give our airplane sufficient time to plan and execute an alternative trajectory to avoid an oncoming obstacle, versus, say, a quadcopter, which can just turn on a dime. Fixed-wing aircraft needs sufficient warning time. And I wanted it to be cost-effective because although something like LiDAR would be state-of-the-art, it can be prohibitively expensive. So for my project, I explored three approaches: stereo vision, sound localization, and radar. So the first attempt was with stereo vision. It just so happens that the depth accuracy of a stereo camera is proportional to the baseline distance between the two cameras. So while commercial stereo cameras might have a baseline of a few inches or maybe a foot, they don't have very deep depth accuracy. So I figured that I could mount the cameras on the plane's 11-foot wingspan, which would provide enough depth accuracy to detect obstacles in that 50 to 100 meter range. Unfortunately, having such a large baseline came with a drawback. Stereo cameras are extremely sensitive to camera alignment, so having them mounted on either wing made it very easy to shift out of alignment. Most stereo cameras that are sold commercially are sold in one sturdy, small rig. And therefore it was impractical to assume they would stay in alignment during flight when there would be other factors at play, such as wind, the propellers, and other imperfections in the surface of the wings. And this picture in the lower right is an example of what a stereo depth map looks like if the cameras are even just a little out of alignment. It really breaks down the disparity map. So my next attempt was to use sound localization. Modern aircraft all have a unique acoustic signature because they all have propellers. And so my hope was that I could use a custom array of microphones mounted around the airplane's fuselage to look at the time difference of arrivals of another aircraft's propellers to trilaterate its position. And this diagram in the lower right is kind of illustrating that the speed of sound is slow enough such that we can actually measure the difference in time of arrival of a sound at different microphones. And from that and knowing the speed of sound, we can estimate how far an object is from each microphone, similar to how cell phone can be triangulated from cell towers, and this actually is how smart speakers can localize the position of a person by their voice. So I designed a system using 4 microphones mounted around the fuselage of an airplane, and I connected all of those to an FPGA over custom I2S buses programmed in Verilog. I2S is a protocol for communicating audio digitally. It's very similar to SPI. And then I used SPI to communicate that data with a microprocessor. So the FPGA was taking samples from each microphone at exactly the same time using those 4 different buses. And then it sent those synchronized samples over to the microprocessor. And then the microprocessor took that information and passed it along to our computer over USB. And the computer actually used a bandpass filter to look at the results to filter out just the frequency we were looking for. Unfortunately, this principle of sound localization did not generalize as well to propellers as it does for a person's voice. Aerial vehicles produce very periodic noises, leading to phase ambiguities. By this I mean that a propeller keeps repeating the same tone over and over. And so it's impossible to distinguish whether a sound reached one microphone before or after another. And that's what this picture is showing an example of. It's impossible to determine whether the blue signal is slightly ahead of the orange signal or if it's really behind the orange signal. So here's a demonstration of me playing middle C, which is around 260 hertz, and trying to isolate that frequency. And in the bottom of this graph here is an estimation of the relative times of arrivals. And you can see that they jump around, and that's because of the phase ambiguity. It's hard to tell whether one is behind or ahead of another. So the third attempt was to use radar. One of the challenges with this is that commercially available radars are either too simple, too expensive, or they're not FCC approved. And to illustrate that, I included a table here of a feature comparison for radars by OmniPreSense, which sells commercially available radars. And the radars that include both the speed, direction, and range don't yet have FCC approval, which means we can't use them at the competition. While the ones that do have approval don't include the range, which is what we need in order to avoid obstacles. A solution, though, was millimeter wave radar, which uses a higher frequency than those other commercially available radars. And since it has a higher frequency, it inherently has less range. That means it doesn't cause as much interference with as many things, and millimeter wave radars can more easily be approved by the FCC. The Texas Instruments AWR 1642 Boost is the millimeter wave radar we chose. It's designed for automotive applications. And it has a range of 80 meters, which is suitable for MFly because we wanted a range of 50 to 100 meters. And here in the bottom right is a diagram showing the kind of results it would get in an automotive application. And so far in our tests, this generalizes well to empty airspace. So the second part of my project was the Unmanned Ground Vehicle, or the UGV. The objective here was to design a ground vehicle that met certain constraints. It had to weigh under 4 pounds with an 8-ounce water bottle inside. It had to be able to fit inside the airplane's fuselage. It needs to be deployed from at least 100 feet in the air. And it needs to be able to land at specified coordinates and autonomously drive. For full points in the competition, it needs to land within 5 feet of those coordinates. So we went through multiple iterations of the design. Design number 1, the brick. The key idea here was just make something that's robust enough to fall, land, and drive. The problem with this was with the weight constraints, we couldn't make something sturdy and still house all the electronics necessary. So we went on to design 2, using a parachute. The idea here was we could perfectly time the UGV's release from the aircraft because there are differential equations for modeling the drag of the parachute if you know the wind. The problem with this is it requires knowledge of the wind, and the airplane can only measure relative wind speed with a pitot tube, but we can't measure the absolute wind speed, so we can't accurately predict how the UGV will fall. That brings us to design 3, using propellers. The idea here is that we can actually use drone motors and propellers to actively slow and steer the UGV's descent into the target landing zone, and ideally within 5 feet of the landing zone. And so this design in particular uses spring-loaded armatures so that it can fit inside the fuselage, and then when it falls out, they extend so that it can fly with the propellers extended. So there's still work to be done. For the detect and avoid system, that entails filtering out the noise from the millimeter wave radar, so there's still some tuning to be done there. But after that's done, we can pass the results into the path planner, which has already been implemented. And for the UGV, the next step is to refine the mechanical design to make it more easily manufacturable. Right now there's a lot of small moving parts. We also wanted to design a custom PCB with a microcontroller, motor drivers, IMU, and altimeter, which can fit into the mechanical design, rather than choosing electronics and designing the UGV around that. Since we have such tight weight and volume constraints, we want to design the electronics to fit inside our mechanical design. And then we need to develop the controls software, which will be tricky because we're essentially making a drone that's also a car. And that's it for my honors capstone. Thanks for watching.